All right, so I'm going to pick up where we left off last time. We were talking about a particular kinetic situation that is often called rapid prior equilibrium. And this is important for catalysis, especially acid-base catalysis. And we'll talk about this again in the catalysis chapter, but just as well introduce it at this point. So let's imagine we have this alcohol and we're going to do a substitution reaction, but first we need to protonate the alcohol. And let's suppose that protonating this alcohol happens in a fast and reversible fashion, just like proton transfer usually does. So I'm going to have we'll have some forward rate, little kf, and some reverse rate, little kr. And then we'll have some forward rate k1, whereby the water leaves to give us a carbocationic intermediate. And then water is the leaving group here. So now we have another water. And that's reverse. And then we will have some nucleophile come in at this stage. And yeah, let's see. And this will be an irreversible step to give us the substitution product. All right. And actually, this isn't exactly catalysis, so but we can think of other situations. We're not regenerating acid here. In any case, let's we've got the irreversible step there and so on. So we could write the overall rate of this reaction, the appearance of our product P, as dP dt equals K2 times, and we'll call this carbocationic intermediate I, K2 times the concentration of intermediate I times the concentration of our nucleophile. The problem, of course, is that we don't know what the intermediate I concentration is, so we'll do the same steady state approximation as we've done previously. We will let di dt equals 0, and then we simply need to write all of the ways we can have I appear and disappear. I can appear as K1 with our protonated alcohol. Now, I'm not totally sure what to call this, but since it's an acidic species, it's the conjugate acid of this base, we'll call it HA, if that's all right. And therefore, this will be A. I guess if we wanted to be more consistent, maybe this is BH plus and this is B or something like that. Okay, so the rate of formation of that intermediate is a unimolecular process, K1 times BH plus. Then we can have I disappear with K minus 1 times the concentration of intermediate I times the concentration of water. That's the backward step. Or we can have things disappear, K2 times I times nucleophile concentration. And again, we can go through and figure out, we're going to set this equal to 0, isolate the terms with I, factor out I, and simplify. And that's going to give us K1 times BH plus divided by K minus 1 times the concentration of water plus K2 times the concentration of nucleophile. Look okay so far?
Yep.
All right, the problem is we're not going to know how much, we're not necessarily going to know at any given time how much of this alcohol, protonated alcohol, is present. But we are going to know at any given time that the protonated alcohol is going to be in equilibrium with the regular alcohol. And let's suppose that we have a way of monitoring the presence of this in solution, but not the protonated intermediate. So we need to do something here to get rid of, to have this protonated alcohol be in terms that are include starting material and not just some intermediate along the way. Before we do that, I'll just write the rate law by substituting in that intermediate concentration into our rate expression. K2 times K1 times BH plus times nucleophile concentration divided by K minus 1 times water plus K2 times the nucleophile concentration. Notice the general saturation kinetics features that we've seen so far. At really high nucleophile concentration, this reaction is 0 order in nucleophile. So that's what we expect for an SN1 type reaction. Though at low nucleophile concentration, we would see first order behavior in nucleophile. Second, we've got some product inhibition going on. Water is one of the products that happens when the leaving group leaves. And so if our concentration of water is too high, we can go back to the alcohol. This solves a problem that students often get when they're taking sort of a second year organic class. They barely learn about the SN1 reaction. They start with some alkyl halide and they do solvolysis in water to get the alcohol. And then in the next chapter, they turn around and take the alcohol and use acidic conditions to convert it into an alkyl halide. And the question is, how do you do that? And the rate law tells you that if you have a high water concentration, you're going to go, the rate's going to be inhibited, and in fact, you probably go back to the alcohol. So if you wanted this reaction to proceed through to completion, you could do something like remove the water. All right, but let's talk about this concentration term and how we can get it in terms of something that we can put into the reaction. And remember, as we do rate experiments, we're going to do them under conditions, well, when the reaction hasn't gone very far to completion, so we'll measure initial rates. There's an equilibrium constant for the reaction of BH plus with water to give you B, which is your alcohol, and H3O plus. In some ways, you can think of this as the dissociation of this acid. And there's some equilibrium constant, as we framed it above, going from the alcohol to the protonated alcohol. That's K reverse. Right? Going from the alcohol to the protonated alcohol is Kf. So that's going to be here, and then going from the protonated alcohol to the alcohol is Kr. In any case, there's an equilibrium constant, and that equilibrium constant equals the concentration of the alcohol times H3O plus concentration divided by the concentration of BH plus times the concentration of water. And then I can move water concentration over to this side of the equation to give me concentration of B times the concentration of H3O plus divided by the concentration of BH plus. This is now the acid dissociation constant Ka for this acid. You've seen this in more familiar ways. Ka equals concentration of A minus times concentration of H3O plus divided by concentration of HA. Doing the same thing here, it's just a neutral conjugate base and a positively charged acid. Okay? So this is the Ka of the protonated alcohol. So now we can, and that's something that we can know and measure and look up from a table. So what that tells us is that we can substitute protonated alcohol for the concentration of alcohol times the concentration of hydronium divided by Ka. So now I'm going to substitute this back up into here for the rate law. And I want this to be sort of all on the same page, so I'm going to have to, that'll work. So let's take our rate law dP dt. So now we have K2 times K1. Instead of BH, we're going to use B concentration of the alcohol times the concentration of water. And then we're gonna divide by the by the Ka number. It's actually going to be easier to write that out with Ka and an exponent -1 there in the numerator, and nucleophile concentration here. And then the denominator is just the same as it was, K minus 1 times the concentration of water plus K2 times the concentration of nucleophile. So this now gives us a rate law that should make some sense. The rate of the reaction depends on the amount of alcohol. It also depends on the amount of acid. That makes sense. The acid is consumed in this reaction, so more acid should make the reaction go faster. Then it will depend on the concentration of nucleophile, though in a way that could be zero order at high nucleophile concentration. And then lastly, this rate law is going to explain product inhibition by the concentration of water there. All right? So that sort of captures everything that you would have learned about this reaction in introductory organic chemistry class, but with all of the nuances. And you could do this experiment under various sort of pseudo first order conditions. You can vary the pH, you can vary the nucleophile concentration, you can vary the amount of alcohol, and so on. All right, questions about that? Okay. While we're at it, I mean, this isn't necessarily what I was planning on doing, but while we're thinking about this, we could talk about rate laws for catalytic reactions, and we won't get to catalysis till chapter 9, but rather than wait until then, it's maybe useful to talk about it now. So ester hydrolysis is acid catalyzed. So we've got this equilibrium step, which is protonation of the ester. All right, and then you have water attack to give you I think I actually don't want to do ester catalysis, which is the one that I want to do. No, this would work. It'll actually be easiest for us, to consider acetal formation, if that's all right. So go ahead and just scribble that out or whatnot. Acetal formation starting with some aldehyde, and then we're going to use some alcohol, and we'll use some acid. We won't even say what our acid is at this point. And we will first protonate the aldehyde, and then the nucleophile will attack, and let's suppose it's methanol, okay? And then you get this intermediate, and this is the hemiacetal. And then, of course, this continues on. Let's suppose, for the sake of all we're going to do, let's keep drawing some of it. At this stage, A minus removes this proton. You end up with the hemiacetal intermediate, which isn't stable. HA protonates the OH group. Then water leaves. You end up with this weird sort of oxonium ion, which then methanol can attack to give you your acetal. Your protonated acetal, and then we regenerate our acid at the very end, removing that proton from the protonated oxygen. All right, and that regenerates our acid. So it's catalytic, and there are two different ways. I've drawn you one mechanism, but there are other options to consider. For example, let's suppose that this equilibrium here is fast. And then let's suppose that attack of the nucleophile methanol on this intermediate is the rate determining step. Okay? So we won't worry about any of the other steps after this point. We're going to say that beyond this point, the reaction's fast. So we can say, for example, that the appearance of our product, P, and we'll call this K1, K minus 1, R, well, no, let's just call it whatever. The appearance of our product P is going to be equal to K2 times the concentration of our protonated aldehyde, which maybe we'll call RH plus, times the concentration of methanol. Okay? Now, in this description of our reaction, the proton transfer takes place before the rate determining step. Okay? And that's a different kind of catalysis than when the proton transfer occurs during the rate determining step. So what we can do, and we'll do something that's very similar to what we've done previously, we can write out an equilibrium expression for protonation of the aldehyde, some equilibrium constant there, A minus, to give you protonated aldehyde. And we can write the concentration of protonated aldehyde as aldehyde times acid times A minus divided by that equilibrium constant. And then we can plug that back into this equation. So we're going to use these ideas in the future as we talk about catalytic reactions. And the issue of whether we say proton transfer is happening during the rate determining step or after is going to be a key issue. All right. There are more things we could talk about there, maybe some specific examples, but probably the best thing to do is to talk about, I don't know, the subject we're going to talk about now is one of the more difficult ones to understand, but it's actually really useful, and it's going to improve your knowledge and understanding of the SN2 versus SN1 reactions. So when we've thought about reaction coordinates before, when we've thought about reaction coordinate energy diagrams, we've thought about energy here, and then say remember the reaction coordinate represents motion along the direction of a vibration that leads you from starting material to product. If we were thinking about this in terms of a substitution reaction, this, for example, might be leaving group leaves, right? But in some reactions, you've got two different things happening at once, right? You have, for the SN2 reaction, you have leaving group leaves as the nucleophile is coming in. So in that way, we can think of a multi-dimensional energy landscape where along one axis we have leaving group leaving, and along another axis we have nucleophile attacks. And it turns out this is going to be a really decent way of thinking about how reactions occur. And so what we're going to do is try to draw a representation of free energy landscape for a substitution reaction, and we're going to talk about how various changes in structure will alter that free energy landscape. All right? So just so I can be consistent with what I've written down, on the y-axis is going to be, no, what are we saying? Well, z, x, and y, I guess. So along the z-axis, we're going to have energy. Along the x-axis, we're going to have forming of a carbon nucleophile bond. And along the y-axis, we're going to have breaking of a carbon leaving group bond. Okay, so if we think about this energy landscape, oh, I got it wrong. We're making the nucleophile bond. And the axis, this x-axis is going to vary from 0 to 1 or 0 to 100%, describing over here the bond is, the nucleophile bond isn't even sort of formed, and over here it's completely formed. And then here we will have breaking the carbon leaving group bond, where again it's going to go from 0 to 1, totally and completely not broken, fully and completely broken. So let's consider a couple of different reaction pathways for a substitution reaction. And the overall reaction is going to be, let's say you have a methyl leaving group molecule plus a nucleophile, and we're going to go to methyl nucleophile bond and a leaving group. All right. Let's imagine a couple of different reaction pathways. We could break the leaving group, we could break the carbon leaving group bond first and then make the carbon nucleophile bond second, right? Or you could consider breaking the carbon, or you could consider making the carbon nucleophile bond first and then breaking the carbon leaving group bond. I guess I don't like how not parallel those lines looked, but you know, whatever. Let's sort of draw what we would expect for intermediates at these two corners. So at the bottom diagonal corner, we have products, which are the methyl nucleophile substitution product and the leaving group product. If we just break the leaving group bond, carbon leaving group bond, but don't have the nucleophile attack, at this corner, we have nucleophile, we have leaving group, and we have methyl cation. Right? In contrast, if at this stage we make the carbon nucleophile bond first, and then the leaving group leaves, at this point we would have, and you're going to already recognize this as something that we don't really even consider in undergrad OChem. That is some kind of pentacoordinate carbon which overall has a negative charge. And the negative formal charge presumably would be on the carbon, but it could be anywhere. And then the other potential pathway you have is to go somewhere along a diagonal between this corner and that corner, starting materials here, which are, again, our methyl bound to a leaving group and then a nucleophile. All right, so do you see the various pathways we've got? I'll try to trace them out along this sort of reaction coordinate portion of our diagram. An SN2 reaction would presumably involve, remove. An SN2 reaction would presumably involve going directly from starting materials to products with nucleophile carbon bond breaking at the same time as carbon leaving group bond leaves. The SN1 pathway, which I'll write in orange, would be we follow this direction first and then go there. All right, so this is sort of the SN1 pathway. So let's talk about now, let's draw in some of the energy changes as a function of reaction coordinate, and let's suppose that our starting materials are sort of here on our y-axis, okay? So what does the SN2 pathway look like? And especially for the reaction of the nucleophile with the methyl group. We could draw, here's a starting material, then there's some transition state, and then we go downhill in energy to products. And you sort of have to imagine this coming diagonal out at you. Although if we take only this slice, this looks like a reaction coordinate energy diagram for the SN2 reaction. All right? Now let's talk about where we expect the SN1 reaction, what we expect that to look like. So along this axis, this trajectory, for the SN1 reaction, we expect something that looks like this, some high energy transition state leading to an intermediate. So to help us stay oriented, I'm going to redraw this energy axis down here at the corner. I'm not sure this is going particularly well. Do you have any questions about what I'm trying to draw? Go ahead, Tyler.
So I'm just picturing in my head the peak and trough graph you showed us a couple lectures ago. And would you not see there be peaks in the corners for that SN2 graph? Because you have all those charged ionic particles in both those two corners.
Which corners? This one?
That one
and that one?
the other one. Yeah, and it kind of, I'm imagining it going down, and you're just showing us that one ideal vibration line.
Yeah, I'm showing you one pathway across the energy landscape. We'll talk about how these pathways change in relative energy as a function of the structure of your starting material.
And that's going over the saddle point in between two peaks of
Right.
SN2.
Right. Now, we're not actually going to say anything about what the actual high energy points are because we can't interrogate them. So what we'll be dealing with is minima and saddle points. Yeah. So for the SN1 reaction, we expect a minimum at this point, though we expect it to be quite a bit higher in energy. And this is where perspective and imagination is going to be necessary. We expect it to be quite a bit higher in energy than starting materials because it's a carbocation. All right, so that point there is the carbocationic intermediate. That's, we're showing the energy of our carbocationic intermediate up here. And we can draw the reaction pathway from starting material through some high energy transition state that is carbocation-like to get to our intermediate. And again, you have to imagine this as sort of being aligned along the y-axis. To help guide sort of what we're going to look at here, I'm going to shade all of that. And I'll also shade this. So you can think of this as just sort of a slice of the mountainside along the saddle point. All right. Now, why do you suppose I have drawn a transition state going to the carbocation so much higher in energy than the transition state going to the product through SN2? Yeah?
Is that because you're going to a less stable product and the SN2 one just goes right into just one step?
Right, one step, and then the intermediate here is a methyl carbocation. All right, go ahead.
Well, methyl carbocations aren't ultra stable to begin with, so it's going to make sense that that's high energy.
That's right.
And then for the SN2, your intermediate, you're going to like almost like half a bond in between
Yeah.
your leaving group. So you're still going to have.
Yeah, your transition state here actually looks kind of like this, only the bonds are longer. But yeah, you have some bond formation compensating for bond breaking, whereas here you've just had bond breaking. Good. The other reason this transition state is lower than this one for our methyl starting material is just that the thing that really bumps up the SN2 transition state in energy are steric factors for the size of the nucleophile and for the size of this group that bears the leaving group. And for methyl, that's pretty small. So there's less electron-electron repulsion as the nucleophile approaches the methyl group. All right, well, once we get to the carbocationic intermediate, then to get to products, we simply have to make the new carbon nucleophile bond as the nucleophile attacks the carbocation. That's going to involve going up from this minimum here through another transition state, but it's not very much higher in energy, and then down, and I don't know exactly where along this pathway the transition state would be, but going down to products. And if we try to shade things to get an idea of what's in front and sort of what we're looking at, we'll have something that looks like this. Okay, so this peak or this saddle point is the transition state for the second step, though that's not rate determining, and so we don't usually worry about it. All right, so you see what we've got is two different alternative trajectories. And why aren't we worrying about this corner? That corner is, we're not concerned with that because that's not even going to be a saddle point. That's going to be a peak. Carbon is too small for pentacoordinate species to be very stable. They do exist, but under weird circumstances. Whereas if you have larger elements like phosphorus or sulfur or other metals, pentacoordinate is no big deal. You can form stable bonds that way. But carbon, you just, the distances and the size of carbon is such that you can't get close enough to make a stable bond in a pentacoordinate situation. So that pathway isn't really an option for us. Okay. Right, so now that we've set up this two different alternative pathways to traverse a landscape from this valley to this one, the issue of whether a reaction is SN1 versus SN2 is primarily going to be an issue of the relative positions of these transition states, okay? So, as an example, and I got to make sure we're not out of time because I often talk too long. As an example, let's adjust this drawing now for, and we'll go to the other extreme. Let's adjust the drawing now for if our starting material, instead of being a methyl group, were, shoot, why are we not, okay, yep. Instead we're like T-butyl leaving group, okay? Such that the cation here is the T-butyl cation, right. So, based on what you know, what does increased substitution here do to the SN2 transition state? Remember, nucleophiles got to go from the attack from the back, right? You've got methyl groups here. It's a steric problem, right? So that should make the transition state go up, right? So if we put, let's just put a dot here. This was the transition state for the methyl leaving group situation. It's got to go up quite a bit higher for the T-butyl leaving group situation, right? So now I'm gonna erase this and just try to draw our pathway all the way up there and back down. At the same time, what should going from methyl to T-butyl leaving group do to this carbocation? Right, it should go down in energy. So up here we had methyl, down here we're going to have carbocation, and you know, how much it goes down, not such a big deal. And because of the Hammond postulate, the transition state that leads to that tertiary carbocation must necessarily be lower in energy as well. So we're going to have that transition state go down in energy by a similar amount. We have all kinds of craziness going on here, huh? So now our pathway along this trajectory you see how our pathway along that trajectory now becomes more favorable because we've changed the energies of various sort of corners of our plot, right? Okay. Now, the nuanced point that I want to leave you with is often we can represent a reaction like this by imagining, the y-axis, and by simply looking at a square that represents the, imagining the z-axis coming out towards us and looking at a square that represents that, the reaction coordinates. So 0 to 1, 0 to 1, carbon nucleophile sigma bond forms, carbon leaving group sigma bond breaks. The ideal SN1 pathway is, SN2 pathway is here. However, the SN1 pathway is in this direction. So it's just sort of the top-down view, right? And one of the things that people have observed is that not all substitution reactions have the same extent of nucleophile leaving and or nucleophile attacking and leaving group leaving in the transition state. So at this particular transition state, we've got this much nucleophile coming in and this much leaving group leaving. But it doesn't have to be this way. That is, they don't have to leave to the same extent. In fact, we can actually bend this pathway such that the transition state swings kind of in either of these directions. And this is highlighting the idea that there's a continuum between SN2 and SN1 rather than them being two discrete sorts of options. What they have determined is that if you raise the energy of these corners at the 1 points, that tends to push the reaction perpendicular to this SN2 pathway. So imagine a marble sitting here on a sheet, and you increase and you lift up this corner of the sheet. In which direction does the marble go? All right. It rolls away from the increased height, right? So we would get motion in this direction if we made the if we make the carbocation intermediate less stable. All right, and then similarly, if we make the carbocation more stable, we'll see motion in this direction. Okay, so we will, there's more we need to discuss. We need to talk about nucleophile and what its effect is, but this will allow us to make some predictions in terms of how, what the character of a transition state is, and we'll have ways to rationalize whether a reaction becomes more SN1-like or more SN2-like. Yeah?
When you say it rolls perpendicular to the axis, is it like tethered to the 0 point, so it moves with the radius, or is it just moving in a line? Look at all of this.
That's, I don't actually know, and we won't need to know the difference between those two situations in as technical level of a detail as that. Yeah, good. All right, have a good Friday and a good weekend. I will see you on, oh, right, Monday.